All right, well, let's move on. What we're going to talk about in section 6.7. We are going to talk about indeterminate forms of limits. Let's explain what that is in just a bit, as we go through it, actually. Indeterminate forms of limits and how we can approach these in an easier fashion than you are probably used to if you took Calculus 1 at this particular school. So, indeterminate forms forms of limits. Limits. Oh, do you guys remember limits? Yeah. They're back. Woo. Limits are the fundamental idea of calculus. If we don't have limits, we don't have calculus. In fact, everything we do in calculus revolves around limits. And your Calculus 1 teacher should have mentioned that derivatives are essentially a limit idea. It's a limit of a difference quotient. It's a limit of a slope. That's all a derivative is. Remember that? How you took the 2 points. If you watched my previous videos on Calculus 1, I took the 2 points and made them really, 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 really close. Remember that? The idea of really close is instead of 2 points, this one, you can't make it 1. You can't get 1 point because you can't find the slope at 1 point. But you can make it so close that it doesn't make a difference, and that idea is called a limit. And then we find the slope of that. So that limit idea is how we get this idea of calculus. So, we're going to talk about indeterminate forms of limits and how to deal with them. Here's what an indeterminate form is, one of the first ones. An indeterminate form is something like this. If we've got a limit as x approaches some number of a function of x over a function of x, and if when we evaluate this limit, you guys have seen this before, trust me, in your Calculus 1 class, and it gives us 0 over 0. Have you ever seen those before?
Yeah.
Yeah. That's typically where you divide out the largest power in the denominator. Remember that? And when like x approaches infinity and things like this. Well, or you get infinity over infinity, same idea. Well, here we're going to do something a little bit different. This is also when x approaches an actual number and this happens. We can do the same thing here. So, a little bit different from what you were taught. This right here is called an indeterminate form. Of the form 0 over 0. So there's several forms. We'll get to one in just a little bit that's different than this. But in general, these things are pretty difficult to compute. Sometimes they're easy because you can factor, you can simplify, but oftentimes they're pretty difficult. So one idea that someone came up with is instead of looking at directly, let's look at how the derivatives of this and this are behaving. Let's look at how the ratio of those derivatives is behaving. So that idea of the ratio, how the ratio of the derivatives is behaving, gives us the same limit of these functions. It's called the L'Hopital's rule. Say L'Hopital.
L'Hopital.
Yeah, it looks like L hospital, except it's missing a couple letters. So let me show you the idea here. This is not a proof. I'm not going to prove it, okay? I'm going to show you the idea of why it works through examples. So to show you that the answer you get is the same for these two examples, it's not a proof. So I'm going to skip over this proof for L'Hopital's. You need to know that it works. So the idea behind L'Hopital's for indeterminate forms of 0 over 0 is that I'm going to look at the derivative of this guy over the derivative of this guy. I'm going to see how those behave. And the way those behave in relationship to each other or in ratio to each other is the same end behavior as what these things are going to do. Do you follow that? You want me to do an example for you?
Yes.
Okay, here we go. So I want you to look at the limit as x approaches 2 of 4 times x squared minus 4 over x minus 2. Okay, please listen carefully. In order for this next thing I'm going to show you to work, you have to make sure you have an indeterminate form. What do you have to do first?
Indeterminate form.
Indeterminate form, that's right. You have to make sure it's 0 over 0. If it's not 0 over 0, you cannot do this. Is that clear? So you have to make sure. So plug in the number. Shoot, remember that about limits? If you plug in the number and it works, you're good. Just plug it in, you're good to go. So plug it in first. Plug in the 2. What do you get over here?
0.
Over?
0.
That's the problem. So we actually get 0 over 0 if we plug in that 2. So we get 0 over 0. We go, all right, well that's of this first type of indeterminate form. So we can work around that with limits and do things like this. This is what you're used to. What you're used to is doing, all right, well, this is x minus 2, x plus 2 over x minus 2. And if I can get rid of the problem, for instance, if the discontinuity is removable, you have a removable discontinuity, a hole. Remember that from your Calculus 1 class? If you can cross it out, it's a hole. If you can't cross it out, it's an asymptote. So if you can cross out the hole here, the removable discontinuity, then you can find a limit really easily, because limits don't care what happens at the point, it happens right before that. If it's going to the same thing, not at it, but right before it, the limit still exists. That's fantastic. That's what we're using here. So this is, all right, cool. As soon as you cross those out, now can I plug in 2?
Yeah.
Of course I can. This is 16. We okay with that one?
Yep.
We also used some proofs that we found out earlier. So if I had sine x over x as x approaches 0, well, look at this. What's sine of 0?
0.
What's
0.
That's 0 over 0. That's another indeterminate form. You with me? Now, by definition that was proved for you in your Calculus 1 class, we know this. We know that. That was true. Do you remember that one?
Yep.
Whenever you get sine x over x as x approaches 0, the limit of sine x over x is actually 1. I'm not going to prove it to you. It's by the squeeze theorem. It's actually not that hard. But if you want that, again, watch one of the Calculus 1 videos. It's proved on there. Right? So that's proved. Now, please don't do this. Oh, well, Mr. Leonard said anything over anything gives you 1. Anything over itself gives you 1. That's not what I'm talking about, all right? There's an actual proof that goes along with this. Obviously, that is not true for this one. So this is indeterminate, absolutely, and we know this definition. Now, what I'm going to show you is that there's another way to go around this besides factoring, because you can't always factor. Besides using definitions, because there's not definitions for everything. Does that make sense? We're going to use something called L'Hopital's rule. So, here's another idea. This is the big idea. Again, called L'Hopital's rule. Looks like L Hospital doesn't have the S, so L'Hopital. Here's the idea. A limit of a function of x over a function of x as x approaches a is the same thing, same limit as the derivative of f of x over the derivative of g of x. But, please recognize this. This is only if it's what? Only if it's indeterminate form. Only if the original limit is 0 over 0, okay? Also, one more thing, just make a note on your papers here. Am I talking about a quotient rule here? No, it's not that hard. Some of you guys are in the habit of making this math really hard, or way harder than it has to be. I'm not talking about quotient rule. I'm talking about really easy. Derivative of the top over derivative of the bottom. Not a quotient rule. Write that down. Not a quotient rule. So, tell you what, we're going to do these examples one more time. I'm going to show you how this works, and you're probably going to love, if you didn't already love me, you're going to love me right now, all right? Get ready to love me. It's almost Valentine's Day, so I like chocolate. Are we doing 2? Okay, 4x squared minus 4 over x minus 2. Okay, check this out. It's awesome. It's really cool. Here's the things you need to check. Do we have a limit? If I plug in the number, do I get 0 over 0?
Yes.
Yeah, we already have that over here. So what I know is that this is true. My original limit is 0 over 0. L'Hopital's rule is in effect. So what I get to do, and I always put like a little arrow with an L L'Hopital or an H, it doesn't matter what you do. I used L, you can use H. You like H's better than L's?
L rules. L rules.
My last name's Leonard, so booyah. So I use it. The Leonard rule. So here's what it says. You keep everything the same for your limit. Just take the derivative of this. Don't use silly things like product rule because you don't need it. 4 stays there times, what's the derivative of the inside? What's the derivative of this? Stop when you plug in the number and you don't get 0 over 0 anymore. So if you plug in 2, does it work?
No.
Plug in 2. How much you get?
16.
How about that? Jeez. Which one's easier? That one. That's easier. Only if 0 over 0, but then that works every time. Check this one. Limit sine x over x. I made no statement whether this had to be polynomials or any, this works with functions, okay? So if it's 0 over 0, you can do it. If you plug in 0, do you get 0 over 0? Let's try this one. If I do L'Hopital's rule, I get a limit as x approaches 0. Remember, it's not a quotient rule. It's not what we're talking about. We're talking about derivative of the top, your numerator, derivative of your denominator. So what's the derivative of sine x? What's the derivative of x?
1.
Bam. Now, you have to check every single time that you do L'Hopital's rule. You don't just say, I'm just going to do it 5 times and we'll see what we get. Okay, that's not the way this stuff works. You actually have to check it. So, if you plug in 0, do you get 0 over 0? No, obviously not. This is a 1. There's no way this can become a 0. Cosine of 0 is?
1.
Over? Equals. Bam. There you go. So L'Hopital's rule works for polynomials, no problem. Also works for some trig functions. As long, this is the big deal here. As long as you have 0 over 0. Very good. All right, we're going to continue our talk about how to do limits of an indeterminate form. Now, so far, we've just looked at this one. What happens if a limit of some rational function, what rational expression here, equals 0 over 0? If that happens, what we learned is that instead of thinking about the limits of the functions themselves, we can think about the limit of the derivatives of those functions. Again, not a quotient rule, just a derivative of f of x over the derivative of g of x, and figure out what that limit is. And it's going to be the same limit as what we started with. That right there is called the L'Hopital's rule. We've used it a couple times, but we're going to start adding to our repertoire now. We're going to start seeing, well, is there other things that we can do? And one other thing that we can look at is what happens if we don't have 0 over 0, but maybe we have a limit where the functions equal infinity over infinity. Well, consider this. If you have infinity over infinity, then you can actually manipulate this so that if you did, instead of f of x over g of x, if you manipulate it, notice that this is equivalent. If you did 1 over g of x over 1 over f of x. First I need to make sure that algebraically you're okay with this. Do you understand that this is this?
Yes.
Do you see that? So if f of x went to infinity, 1 over f of x goes to 0. Did you catch that?
So you're just flipping the...
That's right. I'm just kind of doing basically the reverse of a complex fraction. Complex fractions say that what you do is you multiply by the reciprocal. This would, of course, be f of x over g of x. It's the same thing, only we're using it this way and saying, well, check this out. If g of x goes to infinity, 1 over g of x, 1 over infinity, would go to 0. If f of x goes to infinity, 1 over f of x would go to 0. What this basically says is that, and you don't have to show this, okay? You don't have to show it. What it says is that if you have 0 over 0, this will work. Also, if you have infinity over infinity, because you can do this, this will also work. So we basically have 2 statements here. We say that if f of x over g of x equals 0, 0, or if we have f of x over g of x equals infinity over infinity, we can do L'Hopital's in either case. Does that make sense? I'm just adding one more condition so that we don't have to change it to 0 over 0. If you ever get infinity over infinity, it's basically the same thing. So a couple little notes for you. I'm just going to rewrite this statement. If the limit of our functions equals 0 over 0, or, now we have a new one, infinity over infinity, then the limit of f of x over g of x as x approaches a is equivalent to the limit of the derivative of f of x over the derivative of g of x as x approaches a. That's the whole thing. That is what L'Hopital's rule says. If you have 0 over 0 or infinity over infinity. Show of hands if you feel okay with this. Okay, a couple other little notes that you need to be aware of. This doesn't just work as x approaches a. This will work as x approaches a from the right or from the left. So remember those one-sided limits you guys did a long time ago? L'Hopital's rule will still work for that. It'll also work if x approaches infinity, both positive and negative. So some other notes here. Also works for x approaches a from the right, or x approaches a from the left, or x approaches positive infinity, or x approaches negative infinity. All those things are fine. So basically what it's saying is that L'Hopital's rule works all the time for whatever you're approaching. Positive infinity, no problem. Negative infinity, okie dokie. A from the right, A from the left, or A altogether, not an issue. So we can use L'Hopital's rule basically all the time. There's only one thing, and it's an important thing that you gotta do before you do L'Hopital's rule. I talked about it briefly last time, but I want to make sure you have this written down. In order to do L'Hopital's rule, you must verify that this, this or this is actually true. You have to have this. So what I'm going to write down is you must check that it is an indeterminate form before you do L'Hopital's rule. Please do that. Big deal. You must make sure you have 0 over 0 or infinity over infinity first. You have to do it. Let me give you an example about why. Give you an example about why. Let's say that I give you the limit of cosine x over x as x approaches 0 from the right-hand side. Look at what's going to happen here. If I plug in 0, remember that this is continuous, so you just plug in 0 and it's the same thing as a one-sided limit. You don't have to worry about that. So just plug in 0. What's cosine of 0? 1. What's this as x approaches 0 from the right?
0.
Is that an indeterminate form?
No.
No, this actually is going to go to infinity. So this thing is positive infinity. However, let's say that we said, oh, well, wait a minute. Can't I just use L'Hopital's all the time? Look what would happen. If I did L'Hopital's rule, I would get a limit as x approaches 0 from the right. What's the derivative of cosine, please?
Negative sine.
Derivative of x?
1.
This would give us 0 over 1, or 0. Did we get the same thing?
No.
No. What this is telling you is that L'Hopital's rule does not work unless you have 0 over 0 or infinity over infinity. That's why this is important. You have to make sure that you have that indeterminate form before you start doing all this L'Hopital junk. Does that make sense? Show of hands if you feel okay with that one. All right, so we can't do it if it's not 0 over 0 or infinity over infinity. Now, when it is, oh my gosh, it's so nice. So I want to practice some examples. They'll gradually get a little bit more difficult. We'll start off nice and easy. I want to make sure that you guys see the concept here. And then, of course, what are we going to be doing all the time? What's L'Hopital's do? It does what over what?
0.
The 0, 0, infinity, infinity. But how do you do L'Hopital's rule? What are you doing here?
First derivative, top and
Derivative of the quotient or top and bottom?
Top and bottom.
Good. So that's really all we're doing is a lot of derivatives. And then checking every time. By the way, every time you use L'Hopital's rule, you want to check again. If it's 0 over 0, you can actually keep going with it. Do another derivative, no problem. Or infinity over infinity, no problem. Keep on going until you can actually solve your limit. That's the idea. You want to see some examples?
Yes, sir.
Okay, let's do limit as x approaches 0, e to the x minus 1 over 2x. Okay, ladies and gentlemen, what's the first thing that you've got to do in order to solve this limit? What are you going to do?
Plug in 0.
Okay, so we got to make sure, we got to verify that it is one of these forms. So let's do that. If we plug in 0, this is, by the way, what you should be doing every time you get a limit anyway. Just plug the number in. Because if it works, you're good to go. If it doesn't work, well, now we have a couple scenarios that we can work with. So if we plug in 0, what's e to the 0?
1.
Minus 1?
0.
So this is 0 over 2 times 0?
0.
Can we use L'Hopital's with that?
Yep.
Fantastic. So we're going to show that. All right, well, let's do a L'Hopital's rule. I know I'm keep asking you, but I want to make sure quotient rule or just derivative of the top.
Derivative of the top.
Just our numerator. So let's do it. Look how nice this becomes. By the way, when you're doing limits, I don't know how strict your Calculus 1 teacher was because I wasn't him or her. I'm definitely not a her, but I wasn't him either. So you need to be writing the limit every single time until you get to actually evaluate the limit. Okay, what you can't do is go, I'm going to ignore that and do the derivative. That doesn't make sense. Okay, you have to have that limit every single time until you actually get the answer. Does that make sense?
Yeah.
You got to do that. So, derivative of e to the x. What's that?
E to the x.
Derivative of 1.
0.
So this is
E to the x over 2.
I love that. Over derivative of 2x is just 2. Now, every time you do a L'Hopital, you reevaluate. You see if it works. If it works, you're done. If it doesn't work, if you get 0 over 0, you keep going. If you don't, then you can't use L'Hopitals. You got to do something else. So, can we plug in 0 here? Let's see. E to the 0 is
1.
Notice, here I have the limit. Here I've actually evaluated. It worked out for me. I don't need to write the limit anymore. Our limit is 1/2. You guys okay with that one?
Is there any time where I'll just keep taking for like a second, third?
Oh, absolutely. You can have multiple, and we're going to get there. Right now I'm keeping it kind of easy.
So you just want to make the variable disappear eventually?
No, not necessarily. Just stick with me here. I'll show you some. Let's look at the limit as x approaches infinity of ln x over x. Now we already talked about this. Is it okay for x to approach infinity with L'Hopital's rule?
Yes.
Yeah, so that's not an issue for us. What is an issue is we got to make sure we have 0 over 0 or infinity over infinity. So let's check it out. If I plug in infinity, let's think about that. What is ln x as x goes to infinity?
Infinity.
Also infinity. Okay. How about x as x approaches infinity?
Infinity.
Is that something that satisfies our conditions?
Yep.
Yeah, it's an indeterminate form. So what that says is, shoot, just do a L'Hopital's rule. By the way, I am not going to be spending a whole lot of time showing you derivatives like these anymore. I'm going to kind of expect that you get that, all right? So some of the chain rules, this doesn't involve chain rule. It doesn't involve quotient rule. It's pretty easy. But just heads up, from now on, I'm probably not going to be showing you explicitly the chain rule. I'm kind of expecting you understand that, okay? So when I have like sine of 3x, I'll probably just be doing 3 cosine 3x, or cosine 3x times 3, and the chain rule is kind of implied there. Does that make sense?
Yeah.
So just to keep it a little bit quicker, because I'm not supposed to teach you chain rule every single time, all right? But if you have questions, let me know. Can you do the derivative of ln x?
Yep.
That's nice. It's 1 over x. Over what?
1.
So derivative of ln x is 1 over x. Derivative of x is 1. Derivative of the numerator, no problem. Derivative of the denominator, got it. Let's plug in the infinity again. How much is 1 over infinity?
0.
So we got 0 over 1. You don't even need the 1 really. It's just 0 over 1.
So it'd be 0.
This is just 0. So this becomes 0. Our limit 0. Do you see how nice L'Hopital's rule makes that? I mean, my goodness, it's so much better, so much easier. Can we do a little bit more difficult ones?
Yes.
Do you guys understand these so far?
Yeah.
Having fun yet?
Yeah.
Do you like this section? You should, compared to some of the other stuff we've done. It's kind of nice. Okay, let's see that one. Limit as x approaches pi of 2 sine squared x over 1 plus cosine x. Tell me again the first thing that we need to do before we start working with this limit.
Let's make it 0, 0.
Let's check that. Is it?
Find out.
Let's find out. Do you know what the sign of pi is? 0. It is 0. So 0 squared is still
0.
times 2 is
0.
How about cosine of pi? How much is cosine of pi?
1.
1 plus -1 is?
0.
Is L'Hopital's rule going to work?
Yep.
Yeah, I made no statement about whether these were polynomials or trigonometric or irrational or square roots or anything. It works all the time. So if we had trig, don't worry about it. Just do L'Hopital's rule again. Remember, it's not quotient rule. It's just derivative of the numerator over derivative of the denominator. So when we do this, show me what you're doing though. Put a little L. Some people use the H for the H part of L'Hopital's. I use the L. I don't know why. Just do. Keep writing your limit as much as you need to until you get down to evaluate. So if we're using derivatives here for our numerator, what's going to happen is this is a chain rule. Do you see it?
Yep.
2 times 2 gives you 4. You'll leave the inside alone. You'll multiply by the derivative of the inside. 4 sine x cosine x. Quick head nod if you're okay with that one. By the chain rule. Good. Now, denominator. What happens to the 1?
Disappeared.
Gone. Can you do derivative of cosine?
Yeah, negative sine x.
Good. I like the negative. That's fantastic. Negative sine x. Also, what should we do next after we've done those derivatives?
Check it again.
I wouldn't check it right now. What I would do is probably simplify if I can. Maybe can you simplify?
Oh, sine and cosine.
Yeah,
maybe
make this problem easy if you can. Do you see sine over sine?
Yes.
Hello.
Oh, 1.
Now, am I doing another L'Hopital's rule right now?
Not yet.
No.
So don't put the L or the H if you're not doing L'Hopital's rule. What we're doing is just we're simplifying, guys. We're not doing anything major. Just a little bit of algebra. We have negative 4 cosine x. There's no denominator at all anymore. Now, after you've simplified, here's where you're probably going to want to plug in the number to see if you get something out of it. So if we plug in pi, cosine pi is times negative 4?
4.
And it's 4. Okay, show of hands if you're okay with that one. You guys getting the idea so far?
Yep.
The idea is check for 0, 0, 0, 0, or infinity over infinity. If you have that, cool. Man, do a derivative of the numerator, do a derivative of the denominator, simplify first, then plug it in again. Repeat process. Okay, number one thing we're doing is we're checking to see if our limit even works. We're plugging in the whatever x approaches and seeing if we have 0 over 0 or infinity over infinity because we can do stuff with that. If we actually get a number, that's easier. You're just done, all right? But we got to check this. So let's plug in infinity. What do we get if we plug in infinity?
Infinity.
Sure, this is definitely infinity. This is 2 times, okay, that's infinity, that's infinity over infinity. Is L'Hopital's going to work?
Yes.
In full effect. So we're going to do a L'Hopital rule here. We'll have our limit, x approaches infinity. So tell me, what's going to happen on the numerator? Can you do derivative of the numerator?
Yes.
Now, let's do derivative of the denominator. What's going to happen here?
Just be 1 over x.
It is chain rule. So derivative of this is e to the 2x times 2 because of the chain rule. So e to the 2x stays there. Remember with chain rule, you're taking the derivative and multiplying by the derivative of this inside part, if you want to call it, the exponent. So derivative of 2x is 2, and then we have that e to the 2x. You guys okay with that so far?
Yeah.
Now check this out. What's that going to give you?
Infinity over infinity.
Can I do L'Hopital's rule again?
Yep.
Yes. Keep going until you can't. Okay? That's the idea here. So notice we're checking again. This is still infinity over infinity, so I'll do L'Hopital's again. If I do L'Hopital's rule again, since I had infinity over infinity, it's an indeterminate form, L'Hopital's works, I get 6x, and I get, let's do the same thing, we'll have another 2, that'll be 4,
E to the
e to the
2x.
2x, again, another 2 because of the chain rule yet again.
B infinity, infinity.
We still have infinity over infinity. Let's do it again. So, We checked for it, we had indeterminate form. L'Hopital's rule, we had it again. L'Hopital's rule, we had it again. L'Hopital's rule, derivative of the numerator is what, please?
6.
Over, what are you going to get on the denominator?
8e to the
So another chain rule, we had a 4. Notice the chain rule is going to give you another factor of 2. That's 8 e to the 2x. Now we're going to check it again. Do we still get infinity over infinity?
No.
No, we get 6 over infinity. Do you guys see it?
Yeah.
How much is 6 over infinity?
It's 0.
It's 0. 0. You have a constant over something going to infinity. That's 0. Now, question, see if you're really thinking. What if this was x to the 31st instead of just the 3rd?
We've been doing it a lot.
You keep doing it 31 times, 32 times, and you're going to get 0 again. Do you see why?
Yeah.
The e to the x is never going to win. So it's going to be infinity no matter what. If you have a polynomial, that's going to gradually reduce down to 0, which is very interesting, isn't it? I would just look at that. Now, you're not going to do this because you're going to show your work. I would look at like a polynomial, something that's always infinity, that's 0, for sure. But you're going to show me more of that, okie dokie? Anyway, that is the idea. Now we're going to make it just a little bit more funner. Funner means harder. Do you guys have any questions so far before we continue? Have I explained this well enough for you to completely understand the idea here?
Yes, does that mean if there's an e over another e, there's no way to ever solve it? Because it'll always be infinity over infinity.
It depends. It depends on what that is. Sometimes you can manipulate that. Sometimes you can
LNs on.
Sometimes you can do other techniques for that. If we come across one, I'll be happy to show you. Which one have we just? Okay. Okay, this one's going to take us just a little while, so stick with me here. What's the first thing you do? You walk me through this. What are you doing here?
plug it in.
Okay, so we plug in the 0. What do we get when we plug in the 0?
You get
Zero.
0, 0, 0
5.
minus 10.
That is not a trivial thing to do. You actually have to show that it is indeterminate, 0 over 0. You guys okay with the 0 over 0?
Yeah.
So if you have 0 over 0, what are you guys doing?
L'Hopital.
Go ahead and do it. So nice it's not a quotient rule, right? These are just, I mean, should be fairly straightforward most of the time. Did you get 3x squared over 1 minus secant squared x? Derivative of tangent is secant squared. Now, what are you going to do here? What?
Check to see if they're...
Do it again. So, we're going to plug in 0 again. What's this go to?
0.
Over. This is 1. Let's plug in 0 to secant. Keep in mind secant is 1 over cosine. Cosine of 0 is 1. 1 over 1 gives you 1. 1 minus 1 gives you... What do you do now?
Keep it going.
Go ahead and do it again. The numerator's cool. Denominator's kind of stinky. It's gonna get kind of bad here real quick. Let's see what's going on. So numerator, hopefully you got 6x. That's pretty basic. Derivative of 1 gives you, that piece is gone. That's nice. Do you see it here? What is that?
Chain rule.
That's a chain rule. That's exactly what we did over here. So we're going to have negative 2 secant x times the derivative of secant x. Follow me on this one. This is what I said I'm going to be doing the chain rule kind of in my head here. So check it out. This is 0. It's gone. This is chain rule. Bring down the 2. So negative 2, leave the inside alone. So negative 2 secant x times the derivative of the inside, which is our secant x. Are you with me? So we bring down the 2, that's negative 2 secant x. Derivative of secant x is secant x tangent x.
going to get secant squared again?
Yeah, we're going to simplify it. You're always simplifying and making this as nice as possible before you move on, especially if you have to do another L'Hopital's. I mean, think about that. There's a multiplication and a you don't want to do a double product rule, right? Make this thing a little bit nicer. So we're not doing L'Hopital's rule, so don't show me you're doing L'Hopital's rule if you're not. We got 0, 6x over negative 2 secant squared x tan x. Well, that was fun. By show of hands, you feel okay with that one? Yes, yes, no? Chain rule, radian 2, multiply derivative inside, leave it inside out. What are you going to do now?
Plug
Let's plug it in. So, plug in 0, what's this become?
0.
What's this become?
Undefined.
I don't even care what this is. This is 0, this is,
Is it undefined?
tangent of 0 is 0. So I don't even care what this is, because this part is 0. Is that clear for you?
Yeah.
So 0 over 0. Tangent of 0 is 0. What do you do now?
Again.
Yay! Go ahead. Do another L'Hopital. Yeah, you're right. It's a product rule. Let's do this together, okay? Do you see the product rule?
Yeah.
Yeah.
Inside the product rule, you have
chain
another
rule.
chain rule, almost exactly like the one we just did. So these things can explode, especially with these trig function like secant. So numerator, man, numerator's nice. We just get 6, like that one. Here we're going to have derivative of the first times the second plus the first times derivative of the second. If you want to do it just below there, maybe that's what I'll do here. Derivative of the first don't forget the C on secant. Thanks to one of you who caught that. Because it just doesn't look right. So derivative of the first times the second plus the first times derivative of the second. I want to double check on my work. Did you guys get the same thing that I got?
Shouldn't there be another tangent in the first one?
Just derivative.
Yeah, you know what? I forgot it. Oh dear, you're right. Maybe I better write it out and take my own advice. Gosh darn it. Okay. Derivative of the first times the second, because we definitely don't want to forget anything, plus the first times the derivative of the second. Thank you for that. Yeah, I did forget one. Derivative of the first times the second plus the first times the derivative of the second. Just take that negative 2 and put it with a secant squared. That's fine to do that. So here, this is very much like this one, just we have a negative 2. So derivative here gives us negative 4 secant x to the first power times the derivative of the inside by the chain rule. We got secant x tangent x. But then we have another tan x. That's right. So negative 4. Leave the inside alone. Multiply by derivative of the inside. The derivative of secant x is secant x tangent x. And then we have that tangent. I just show of hands feel okay with that one, just to make sure. Okay, good. Moving on. Let's change that to a minus. Minus 2 secant squared x times derivative of tangent is another secant squared x. Whew. Okay, if we put everything together, we have negative 4 secant squared x tangent squared x minus 2 secant to the 4th x. It looks nasty. It's not that bad when you really think about it. First, I want to know, are you okay with this part?
Wait, isn't the secant cubed?
What did I do?
Because you have to leave the answer alone.
No, it should still be secant squared. The chain rule brings us 2 down. So you have a secant times a secant gives you secant squared.
Oh, okay.
It's secant squared tangent squared. This is correct. Okay, good comment. Any other comments or questions? Are you seeing, ladies and gentlemen, where everything's coming from? You kind of shut up on me here for a little bit. Are you okay with it?
Yeah,
You're like, oh my gosh. Are you all right with it? It's trig, but we know derivatives, right? So we know chain rule, we know product rule, we know derivative of secant and tangent, so we should be okay with this stuff. Secant squared, tangent squared, secant to the fourth. Now, what do we do here?
Plug it in.
Does the 6 change?
Nope.
Don't worry about this because it's connected to this. What's tangent of 0?
0.
So this whole piece, 0. Now, we already did secant x, where x is 0. How much is secant of 0?
1.
It's 1. How much is 1 to the 4th power?
1.
Times negative 2. Remember, this whole thing is 0.
All negative.
So what this is, we stop writing the limit because we're done with the limit. We have 6, we've actually evaluated. Over negative 2, our answer is negative 3. That limit's negative 3. Okay, that's pretty bad, but I wanted to give you a hard one. That way you understand how to deal with this. I don't want to give you all easy ones and then you get your homework and go, oh my goodness. So this is a little difficult, right? Stick with it. All this is check for 0 over 0, check for infinity over infinity, and then do L'Hopital's rule until you can't do it anymore. After that, hopefully, you can evaluate your limit. Show of hands if you feel okay with these ones. Now, that's all well and good, but sometimes, bless you, we're going to have some different indeterminate forms. So I want to check those out. So question is, what about the cases where we have infinity minus infinity? What about the cases where we have 1 to the infinity? Or 0, infinity to the 0, or something like that, something crazy. Well, if ever you get this where you have infinity minus infinity, something that, don't do this. Well, infinity minus, that's 0. Infinity minus infinity, hey, 0, done. No, we can't do that. What you have to do is somehow manipulate this until you get 0 over 0 or infinity over infinity. So usually what that is finding the common denominator and making one fraction out of it. Does that make sense to you? So if you have this, what about this? We're going to use some algebra. To get either 0 over 0 or infinity over infinity. Same thing happens with this. If you had infinity times 0, something like that. If you got infinity times 0, oh my goodness, don't just say that that's 0. I know it seems weird, but that's not always the case. We actually have to manipulate it to get infinity over infinity or 0 over 0. This one's typically pretty easy, and I'll show you that. So quick example. Let's look at the limit as x approaches 0 from the right-hand side of 1 over x minus 1 over 1 minus cosine x. Oh, goodness. Hey, what's the first thing that you should be doing on limits?
Plug in the 0.
Let's do that. Let's plug it in. If you plug in the 0 from the right-hand side, from the right, it's from the right because this limit doesn't exist unless we go one-sided, okay? Because it does this. So you can't say at 0, I had to give you a one-sided limit for this specific case. Are you with me on that one? So from the right, this thing goes to infinity. This is infinity. This thing goes, well, this is 1 over 0. That thing goes to infinity. So we have infinity minus infinity here. Do you guys see what I'm talking about? All right. If we got infinity minus infinity, we don't just say it's 0. We got to work on this. And one good way to work on this is if you have two fractions, man, just make them the same fraction. Put them on one fraction. Because then if you can get 0 over 0 or infinity over infinity, you got L'Hopital's question.
So 1 over 0 is also 1 over, would it be infinity?
1 over 0 is infinity. That's right. As we go to the right, that's a positive number, correct? So we have 1 over a number going to 0. So this is from the right. These are positive numbers. So from the right, it's going towards 0 this way. It's doing this. The graph is actually doing this, but x itself is getting really close to 0, but positive. So if you're taking a number, a constant number, dividing by something really close to 0, that's going to be infinity. It's It's going to infinity question.
So that plus is what's giving you the infinity, right? If that plus or minus wasn't there, you just plug in 0.
You have to think about the graph if you're going to do it graphically. This is the graph going from the right-hand side, not to the right-hand side, from the right-hand side. It's going this way on this graph. That's how that looks like. We're going this way. Hey, what's happening to my graph when I'm going this way? It's doing that, positive infinity. If that was a minus, it would be negative infinity. Does that make sense? If it was this, the limit would actually exist. We could just say at 0 because the limit would be positive infinity. They're both going that way. You with me on that one? Okay. Shouldn't have done that. That was just a recap of limits, but hopefully that helped you. All right, so maybe one thing we can do is make this one fraction. Get everything in one fraction, get a common denominator, and then see what we got. So if we do that, notice I'll have to multiply by x over x. I'll have to multiply by 1 minus cosine x over 1 minus cosine x. You guys with me on that one?
Yeah.
So we're going to get out of this is 1 minus cosine x minus x all over x times 1 minus cosine x. You guys okay with that one? You sure? Just some algebra, just some common denominator stuff. We're multiplying by 1 minus cosine x over itself and x over x. That's why we're getting 1 minus cosine x from here minus x when we multiply by x. The denominator is going to be the same. One more thing I'm going to do, I'm going to distribute this because if I have to do L'Hopital's rule, I'd rather deal with a smaller product rule than a bigger one. You can do either way. You know what? You want to leave it this way? We can leave it that way.
No.
Fine, okay. So I'm going to distribute that, and I'm going to get x minus x cosine x. Still okay with it?
Yeah.
Hey, what's the next thing that we should do?
Plug in.
Let's see. If we plug it in, we get 0. So plug in 0 here. How much do you get?
1.
1 minus 1 is?
0.
Minus
1.
0.
Oh, 0.
this whole thing is?
0.
This is 0. This is 0. Doesn't even matter what this is.
That'd be
0 minus 0 is?
0.
Do you guys see that this is 0 over 0?
Yes.
Yeah.
This is another L'Hopital rule. Let's go ahead and see if you can do the L'Hopital rule. I'm going to do it on the board. This one should be pretty easy, pretty straightforward. This one, you're going to have, what are you going to have here? Not a chain rule.
Oh, that would be a product.
That's a product rule. Keep in mind when you're doing the product rule, I'll show you in a minute. Let's see if you catch it. Go ahead and do it. What's the derivative of 1?
0.
What's the derivative of cosine x?
But is that negative cosine x?
So if this is negative, so we'd have negative sine x. Negative would be, this would be positive
Yeah.
sine x. Are you okay with that one?
Yeah.
How about this? Nice one, yeah. Did you already take care of the derivative at the bottom? Okay, work on it. I'll give you another minute. If you're going to do this product rule, put a bracket up there or something, because when you subtract, that minus sign will have to distribute. You catch that?
Yeah.
So we're going to have derivative of the first. Hey, that's not a big deal. So derivative of first is 1 times the second plus the first times the derivative of the second. This, hey, that's 1. Minus, we got a minus. We put a bracket up there. Derivative of the first is 1 times the second cosine x. Plus the first, leave that alone. Derivative of the second is negative sine x. Of course, I'm assuming you know how to do product rule really, really well, right?
Yeah.
All right. So moving on. What are you gonna do with this stuff?
Distribute the negative.
Yeah, probably. I would probably move this here, then distribute the negative. So
Yeah.
we'd have a limit as x approaches 0 from the right. We'd have sine x minus 1. Notice, we're not doing any calculus right now. We're not doing any, we've done just a common denominator. We've done L'Hopital's rule here. But now we're not doing anything. We're just kind of combining some stuff. 1 minus cosine x. What's that sign going to be?
Positive.
Minus.
No minus.
Wait.
Positive, yeah.
Ultimately.
Distribute it. Be positive, yeah.
Would.
Yep, it's going to be a plus. That would change this to a minus. That changes it back to a plus. Okay.
Did it all at once.
All at once. Do all at once. Now what are you going to do?
Plug in 0.
Let's do that. So if we plug in 0 here, look at sine's it's continuous. So the limit as x approaches 0 from the right is the same as the limit as x approaches 0. No big deal. So just plug in 0. What's sine of 0?
0.
Minus 1.
-1.
So we're not getting 0 over 0 here. So we can't do L'Hopital, whatever happens, we can't do L'Hopital's rule after this. Are you clear on that?
Yeah.
We can't do it. So this is going to give you -1. On the denominator, let's do this. I've got a 1. How about cosine of 0?
1.
Minus 1
Plus
plus
0. So it'd be -1 over 0.
negative 1 over, okay, so
Negative
negative
infinity.
1 over, what's that going to be?
Negative infinity.
Negative infinity. Exactly right. Show of hands feel okay with that one. That's a little weird, but my point is that when you get down to this, you can't do L'Hopital's rule anymore. You can't just go, I just want to do it again. It doesn't work. I already proved that to you. So we have to actually manipulate this and see what happens here. Once you're done with 0 over 0 or infinity over infinity, just find out what the limit is. Work it through like you already know how to do. Okie dokie. Let's tell you what, I think we'll do one more and then I'll show you a different indeterminate form. Oops, I'm sorry, that's not a limit, it's ln. Yeah. Sometimes all it takes is just a little manipulation to make this thing look the way that you want it to. So for instance, if we plug in 0 right here, does anybody know cosecant of 0? Remember that this is 1 over sine, correct? How much is sine of 0?
0.
So this would be 1 over 0. How much is that?
Infinity.
That's infinity. This one, if I plug in, what's sine of 0? 1 minus 0.
1.
ln of 1.
0.
This is infinity times 0, is what this is. Do you guys see what I'm talking about? You
Yeah.
gotta do it. You gotta think through it. But this is infinity times 0 is what that is. Can you do infinity times 0 the way it is right there?
No.
No, you don't put infinity. You don't put 0. We actually have to do the work. This is going to be kind of interesting to see that it's not going to be either one of those two numbers, infinity or 0. So this was infinity because it's 1 over sine. This is 0 because we have ln of 1. All right, well, you know what? Let's just think about what cosecant actually is. Cosecant's what again?
1 over sine.
So if this is 1 over sine, then we can change this limit into ln 1 minus sine x over what, please?
Sin x.
Did you guys follow that? Cosecant is 1 over sine. Therefore, if cosecant is 1 over sine, you're just multiplying 1 over sine x times ln of this nasty stuff. we're going to get ln of 1 minus sine x over sine x. Can you simplify the sine x's?
Not yet.
No.
Oh, heck no, not at all. What should you do right now?
Just plug it in.
Now,
Plug in the 0.
if you plug in the 0, hopefully you see this. This isn't going to change. This is still going to be 0. We didn't change that one at all. This one, well, because we changed an infinity down to a denominator, that's going to be how much?
0.
That's 0. This is 0 over 0. Now what can you do?
L'Hopital.
Yeah, you do L'Hopital. So just by changing some things around, make it something different. Make it 1 over sine instead of cosecant. Hey, no big deal. Then it becomes 0 over 0. Now you have to be okay with that one. It's a little manipulation here, so we're changing these problems little by little. Go ahead and see if you guys can do the L'Hopitals on this. Oh, goodness. So we had infinity times 0. We said, hey, this is fine. I like that one. This one, let's rewrite it a little bit. Cosecant is 1 over sine. Therefore, we have ln over sine, and that gives us 0 over 0. That's why we're able to do L'Hopital's rule. If you do the L'Hopital's rule here, one of these parts is really easy. What's the derivative of sine x?
Negative cosine.
I'm sorry, what's the derivative of sine x?
Cosine. Alright.
Do you remember how to do the derivative of ln?
1 over the inside, derivative of the outside.
What do you have to use here?
Chain rule.
90% of the time, you're right. Yay! Chain rule, that's right. So we'd have 1 over inside,
And negative cosine.
1 over the inside, times the derivative of the inside. Let's look at the derivative of the inside, everybody. Derivative of 1 is?
0.
Derivative of sine?
Cosine.
So we're going to have negative,
Cosine.
that's right, negative cosine x. Show of hands, feel okay with that so far? You sure? Don't plug anything in yet. Don't do that. What I want you to do right now is simplify. Right after you do this, simplify if you can. Do you see something that simplifies?
Cosine x.
Cosines are done. Yeah, they're gone. So if we simplify our cosines, wow, the problem that looked like it was going to be really hard becomes really easy. So we get no L'Hopital's rule. We don't have to do that. We're just simplifying here, folks. You're not always doing L'Hopital's rule. This only took one of them. So we're going to have a limit. As x approaches 0 from the right, we got negative 1. See where the negative's coming from?
Yeah.
Over 1 minus sine x. And now we should try to do that, do the plug-in. Now we should try to evaluate the limit. Since we have negative 1, we know that L'Hopital's rule will not work anymore. Hopefully this thing will work for us. Sine of 0?
0.
1 minus 0?
1.
So we have negative 1 over 1. We have negative 1. Negative 1. That's the idea. Quick show of hands, feel okay with that one. Now, sometimes, and this is where it gets a little bit more interesting. It really is more interesting. These are fun and good and all, but they actually get kind of tedious. And I know that's 0 over 0, no problem. We're good. Sometimes we get some really interesting things, interesting limits, and we can do something pretty cool with them. It's probably going to blow your mind a little bit, like a mind grenade. You ready for it? What if I asked you to do the limit as x approaches 0 from the right of this? And you go, wait a minute, what now? Where's x going to?
0 to the power of 0.
So this is 0 to the power of 0.
1.
No.
Be 1.
0 to 0 is not 1.
What is 0 to the 0?
0? I would say 0.
It's indeterminate.
Ah, it's indeterminate because we don't know. Because you go, oh, well, anything that's 0 power is 1, okay, but 0 to any power is 0, so what do we have?
Oh, God.
Which one? 0 or 1?
I don't know.
Crap.
Schrodinger.
Let's
0.
make up something that will work. We're just going to make up our own math here, okay? Let's make up something that will work. I'll give you a note, and this is probably where we'll end it, and I'll start here probably next time, but look at this. For any limit, if you have a function of x raised to another function of x, can you please verify that's exactly what I have going on here? Yes, no?
Yes.
Function of x raised to a function of x. I'm not talking about x squared here, okay? I'm talking about x to the x, something with an x here. If this equals 0 to the 0, or infinity to the 0, or 1 to the infinity, if it's one of those, try this. This is interesting. Instead of thinking this as f of x to the g of x, we can actually do a little trick here. It's the same trick, I hope you remember this. It's the same trick that we did with logarithmic differentiation. The same idea, only we can't just put ln. Here's what we're going to do. We're going to say, hey, you know what? This, good board. This was the same thing as this, wasn't it?
Yeah.
Okay. Therefore, this is the same thing as this. Do you believe it?
Yes.
Now, what does that allow you to do with that g of x?
Bring it out.
Bring it out front.
Yes. So then this becomes e to the g of x ln f of x. That's the idea here. Let me show you the way this works in practice. I'm just going to give you the first little part, and we're going to call it good. We'll finish this problem up next time. But so, can you guys verify that right now I have 0 to the 0?
Mhm.
Not a good thing. So what we're going to do instead is we're going to write this as e to the ln of x to the x. Only I'm not going to leave that x there. What am I going to do with that x?
Bring it out front.
So then this is limit x approaches 0 from the right, x ln x. Are you okay with that one? Now there's one more interesting thing about this. Because e is continuous, because e is that constant base continuous, I can actually pull the e out of the limit. This is equivalent to this. Instead of taking limit of e as that approaches, I can do e of the limit as x approaches 0 from the right of x ln x. So what that means is this. Listen carefully. You ignore the e. Ignore the e. Just work on this limit, figure it out, and then put it back as an exponent of e. Does that make sense to you?
So it's like a constant pulling up.
Kind of like that. E is continuous, so and it's a constant base. What that means is that the limit of e to a power is the same thing as the limit of the power, and then take e to that power. Same thing. So what we're going to do here is we're going to rewrite these things, all three of these forms, as something like this. Work on this limit, and I'll show you how to do that next time. This, by the way, is 0
times 0.
times infinity, negative infinity. So we rewrite it using some of the stuff that we just did, 0 times infinity, and then put that as a power of e. And that's all we've got to do. Does that make sense to you?
Yeah.
I'll show you more on that next time.
So
All right, we're going to continue. So what we're talking about in section 6.7, of course, is the indeterminate forms. And what we know is that if we have a limit of a rational expression somehow, not even polynomial over polynomial, just any sort of fraction, where our limit is, and we've checked it, we plug the number and we get 0 over 0, or we get infinity over infinity. Those two cases, then we can do L'Hopital's rule immediately. We just take the derivative of the numerator, we take the derivative of the denominator, no big deal, that's it. So 0 over 0 or infinity over infinity. Of course, one big thing we found out last time was we had to check that. It doesn't work if it's not 0 over 0 or infinity over infinity. Does that make sense to you?
Yeah.
Now, what we're doing here is we're discovering there's a few more indeterminate forms. The last thing we did last time was infinity minus infinity. When you have that, it's a really good idea to make one fraction, because then most of the time it changes to infinity over infinity or 0 over 0. You remember that problem? Had a cosine in there, I believe. Or if we have 0 times infinity, okay, rewrite one of them. That way you have infinity over infinity, or 0 over 0, no big deal. Now we're looking at some special cases of when we have a function of x raised to a function of x. And one thing we learned, the very last thing from last time was, well, if you have a function of x raised to a function of x, we can always rewrite this. Just use e to the ln. Remember that e to the ln is is an identity that gives you back exactly what you have. I think I gave you this one last time. 2 equals e to the ln 2. Every time. That's the idea. 2 to the x would equal e to the ln 2x. No problem. That's basically the idea that we're doing here. We're saying, all right, well, if I have a function of x raised to a function of x, do this with it, and I can move that function of x down front. Now, as far as our limit goes, that says that when we get something that we can't actually really do directly, I mean, think about that. We always try to plug these in, correct? Always. So if we take our 0, plug in 0, what do you have? 0 to the
0.
We got that. Something that looks just like that. Let's try this, and let's see what we can do with it. So this is the same thing as a limit as x approaches 0 from the right of, well, it says that we're going to take e to the ln. This is just an identity statement that says you can write anything as e to the ln of that thing. E to the ln x to the x. Now, why do we do this? What's it allow you to do again?
Pull that x up.
That's the idea. Get rid of that exponent. So we have a limit as x approaches 0 from the right, e to the x ln x. Now there was one more thing I told you last time. I'm not sure if you remember. I know we were kind of rushing because we had like 2 minutes left when we were doing this problem. Do you remember what I can do with the e? That's right. We don't really take it away where it's gone forever, but we take it away out of the limit, absolutely. So with this, we can actually write it, instead of the limit of e to this expression, we can write e to the limit of that expression. So basically, we're going to ignore that e for a little while. No problem. We're just going to look at the limit as x approaches 0 from the right of x times ln x. Show of hands if you feel okay with that one. Now, take a look at the limit as x approaches 0 of x ln x. What do you get when you plug in 0 from the, remember, from the right means going this way. It's going towards the left. It's from the right. What do you get here? What do you get here? You get 0. What do you get here? No, you don't get 1. You get negative infinity, that's correct. So this is basically 0 times infinity. I'll give you a real big hint here. If you ever get something like 0 to the 0, ln of 0 is going to become negative infinity. You're going to get something like 0 times infinity. What you're required to do here, and this happens almost all the time with us, okay? What you're required to do is just rewrite this piece. Can we do 0 times infinity? No, we can't do that. That was one of those indeterminate forms we dealt with last time. So rewrite just this little piece. Here's the idea. The piece which is easier to take the derivative of, you're going to move that to a denominator. You're going to make it a denominator. It's hardly ever the ln. Hardly ever this. It's typically this one. Let me show you what I'm talking about. So again, we can't do 0 times infinity. What we can do is 0 over 0 or infinity over infinity. Does that make sense? So if I have 0 times infinity and I make the 0 go to a denominator, it's going to become another infinity. It's going to change 0 times infinity into infinity over infinity. Does that make sense to you? So we're going to change the look of this a little bit. By the way, I know I already said it, but you make a little mental note here. We hardly ever change this guy. The reason is, you're going to see in a minute, this would be hard to take a derivative of when it's on the denominator. This one is easy, okay? So check it out. Do we still have an e?
Yes.
It's going to be there the whole time. I would recommend to you that you keep on writing it. That way you don't forget about it at the very end of your problem. Go, my goodness, how they're getting 1? I got 0, okay? So we got e, limit, don't forget the limit. X approaches 0 from the right. Leave the ln x. Make this thing become a fraction. You can always make an expression become a fraction if you take it and put it under 1. So instead of x, you could write this as 1 over x. Isn't this still technically, can't you move that to the numerator? From this denominator to the numerator? Then this is valid. This is exactly the same thing. Show of hands if you feel okay with that one. Now check out what happens. This is going to make sense about what I just explained to you. If I take 0 now, look at this. If I take 0 from the right, ln of 0 from the right,
Negative.
This is negative infinity. You need to understand the look of the graph of ln. ln looks like this. Does that, okay? So it's going negative infinity. As we approach 0 from the right, it's going negative infinity. So this is negative infinity over, check this out, look what happens here. If I take 0, what's 1 over 0?
Infinity.
This counts, by the way. Negative, that's fine. Negative infinity over infinity counts as infinity over infinity. Hey, can I use L'Hopital's rule with this now?
Yeah.
Yeah, as soon as I change it to this, that's great. Could I do it here? There's not even a denominator. How would you do that? So make it have a denominator, check it, make sure you get 0 over 0 or infinity over infinity. Do I have to switch any of this around? Do I have to switch any of this around? Heck no, it's infinity over infinity, that's fine. Just start L'Hopital's rule from right here. 0 over 0 or infinity over infinity. Are you guys clear on that one? Well, let's do it. So that was perfect. Now let's do a L'Hopital. I still got an e. Nothing's going to change about that. I still got a limit. 0 from the right. How we do L'Hopitals, hopefully the last time I'm going to explain this, so we take the derivative of the numerator, we take the derivative of the denominator. It is not a quotient rule. So let's do the derivative of the numerator. Everybody, derivative of ln x.
Times 1.
Cool, okay, so 1 over x, no problem. How about the derivative of 1 over x? All I heard was blah, 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 blah. What I'm hoping you said is, yeah, that's right. I heard you that time. You don't have to get attitude with me. Jeez. Yeah. So this derivative is 1 over x, yes?
Oh, you put it on the bottom.
This derivative is negative. Do you see why it's negative? You think about this as x to the negative 1, okay? X to the negative 1 goes down, subtract 1 from the exponent, it becomes negative 2, negative 1 over x squared. Quick head nod if you're okay with that one. Now, before you go any further, of course, our idea is simplify before you do another, or before you try another L'Hopital or whatever you're going to do. Simplify these things. So can you simplify this stuff? Of course. So no L'Hopital's rule, we're just going to simplify. E still there, limit still there, as x approaches 0 from the right. Let's see, this guy would become 1 over x times, remember that when you have a complex fraction, instead of division, we can multiply by the reciprocal. Can you simplify that?
Negative.
That's really nice. Yeah, negative x. Okay, so we have now e to the limit as x approaches 0 from the right of negative x. E to, hey, can we take that limit now? Can you do limit of negative x as x approaches 0 from the right? How much is it?
0.
The whole,
0.
plug it in. How much is it?
0.
0. So, e to the, this is why you don't forget to write the e. I think I said it earlier. If you're going, man, if you forget to write the e on all these things, you go, okay, I just forgot to write it, and then you're going to get 0. You go, wait a minute, they're getting 1 in the back of the book. How in the world are they getting 1? I'm getting 0. Well, because you're forgetting the e. You don't just take ln, we do e to the ln. So the e's got to be here, and the e's got to be here, and the e's got to be here, making this a 1. Interesting, isn't it? 0 to the 0 in this case is going to give us 1. Show of hands, feel okay with that one. Good, all right. Does it make sense? Cool. Tell you what, we're going to only try 2 more. These are a little bit more complicated. I'm going to try to give you some really difficult problems. That way we can work through them together, and you can see all the ins and outs of all this stuff. These are what I would consider to be hard ones. Question?
Would we simplify something, like say we were to simplify that and it didn't come out to be something as easy as x, could we continue doing L'Hopital's rule, or?
Absolutely. Look, at L'Hopital's rule works every time you have 0 over 0 or some form of infinity over infinity. Okie dokie? So as long as you still check that, as long as it's still indeterminate, you can do L'Hopital's rule. It's not just a one and done. All right. So if it didn't work out nice and you had like if you had 1 over x, now you couldn't do L'Hopital's rule there because it'd be 1 over 0. That would be infinity. You'd have e to the infinity, it would be infinity, okay? But you can do L'Hopital's rule as long as you simplify it and it's still, or you can manipulate it and it's still 0 over 0 or infinity over infinity.
Are all the problems involving the e's always going to turn out to be 1?
Nope. No, not all the time.
Can be e to something.
A lot are, some are, but some aren't. So no.
Alright.
Okay, let's give this a try. I know this one's it's gonna be a little bit more difficult. That shouldn't be a problem for us. I want you guys to kind of lead me on what you would do, how you would think about this problem. Because right now, honestly, we only have 2 more examples. So you guys should be kind of pros at this point. Kind of understand what's going on. What would you do first?
Plug in the pi over 2 and see what.
Let's see if it works. What's tan pi over 2 from the left? Not to the left, from the left. This way. What happens here? Say what? Positive infinity, that's right. Do you know the graph of tangent? Do you have any idea what it looks like?
Like a,
This is pi over 2 from the left. Okay, how about cosine of pi over 2? We had to go from the left on that one because for tangent it would be undefined. The limit wouldn't exist if I said the limit at pi over 2. You can't do it because one does this, one does this, all right? So I had to say from the left. That's defining that. The cosine doesn't care because it's defined from the left, it's defined from the right, so therefore it's defined in both of them. It goes both. In each case, cosine of pi over 2 is what?
0.
Good. So this is infinity to the 0. Is it one of the indeterminate forms that we can work with?
yes.
Look over there. Is it one of the indeterminate forms that we can work with? Yeah. Now, here's the idea. If I didn't mention it before, here's the idea. We are always trying to get this down to the form of 0 over 0 or infinity over infinity. Not sure if you understand that concept. We can't do anything with this right now. We can't do anything with that. So we're going to work with it. We're going to use probably this technique. That's why I said try this for each of these cases. Try doing this. It'll help you. Because if you can do this, if you can rewrite it as infinity over infinity or 0 over 0, then we can do a L'Hopital's rule. So we're always trying to work with these things to get them down to an indeterminate form, which we can work with. So changing this type of form into 0 over 0 or infinity over infinity. Okay, now that we have the idea, tell me the next step, please. What would you want to do? Okay, let's all do that. You know what? You could even do it right now if you get the hang of it. You could write e to the limit cosine x ln tan x. You guys see that? That's what we're going to get ultimately. I'm going to show you the steps, but you could do it right now. That's what I would do if it was my paper. I'd write e to the limit cosine x ln tan x. So e ln tan x cosine x. The two things we're going to do, which is why I said this earlier, if you get in the pattern of this, because you're going to do it a lot, okay? Yeah, this moves down all the time, doesn't it? That exponent moves down all the time. This e comes out all the time. So we end up getting e outside of our limit to the limit x approaches pi over 2 from the left cosine x times ln tan x. You know what? Every step that you do, you got to check what type of form you're working with now. So let's see if this works. Okay, always be checking to see if it works. Pi over 2. Let's do this. Well, how much is that? 0. It's not going to change what's happening, right? We just want to check the form to see what we can and can't move. So that's 0. How much is that? That's infinity. ln of infinity is still infinity. Which one would? Well, I'm sorry. I should ask you this. What should we do now?
Move one of them to the bottom.
Move one of them to the bottom, okay. Which one are we gonna move to the bottom, the ln or the other one?
Cosine x.
Yeah, it's rarely the ln, because if you imagine this from over here, if I move this to the denominator, I get 1 over ln x. You with me?
Mm-hmm.
That's really hard to do. 1 over ln x would take the derivative of 1 over ln x. That's going to get a little difficult, okay? We'd have a chain rule. We'd have ln x to the -1, we bring in the -1, you have -2, and then we have a chain rule after that.
But it's possible.
It won't work out for you. It's possible to do. You can do the derivative of 1 over ln x, but it's not going to work out like this. Okie dokie. So, I'm just going to give you the hint here. You're rarely, if ever, going to put this one on the denominator, because you're going to get lots of chain rules that way. Does that make sense to you? This one is the one we're going to move down. We might get a chain rule, we might not, but that one's going to be easier than the ln in most cases. So we still have the e. We still have a limit pi over 2 from the left. We got ln. We got tan x. We got 1 over cosine x. You guys okay with that so far? So you can do that every time. You say, hey, cosine x, no, let's just put it over 1 over cosine x. It's the same idea. Now, of course, we can simplify this a little bit. Maybe we don't want to work with 1 over cosine x. We might want to work with 1 over cosine x is what? 0. Let's call it secant. Okay, now that we've done that, now that we've done one more step, let's check to see what type of a form we have. Hopefully, this process, it should work for you guys. It should make it a 0 over 0 or an infinity over infinity. Let's see. Now, this shouldn't have changed from here. This should be the same. So when I plug in pi over 2, tan from the left, tan x is still infinity, correct? That means ln of infinity is still infinity. This is still infinity. Secant x, as x approaches pi over 2. Remember that this is 1 over cosine. How much is cosine? Remember, it was this. How much is cosine of pi over 2? 1 over 0?
Infinity.
So this is infinity over some form of infinity. Can we do L'Hopital's rule right now?
Yes.
Then do it. Hey, what are you going to have to do for your derivative of ln tan x? What is that? 90% of the time, that's the correct answer. That's right. Yay! Let's see if you knew what you were doing here. Ladies and gentlemen, the derivative, remember this is not, thank goodness, this is not a quotient rule. What's the derivative of this guy? Secant x
Squared.
tan x.
Oh,
Here, how we do derivative of ln is 1 over the inside times derivative of inside. So we have 1 over inside, here's 1 over inside. Got it?
yeah.
Times derivative of inside. What's the derivative of tan x?
Secant squared.
So we have secant squared x over tangent x. Show of hands, feel okay with that so far. 1 over inside, that's where we get the tan x from the denominator, times derivative of inside, that's our secant squared. What do you think we should do now?
Check to see if it's still 0, 0.
Should we check it or should we simplify it?
Oh.
Yeah, you're going to simplify it first. Before you start checking again and again, let's simplify it. So can you simplify that?
Yeah. Well, yeah. And secant.
I'm going to take a little side road here. So we have secant squared x over tan x, right? Times, if you put this over 1, if you put that over 1, division's the same as multiplication of the reciprocal. So we would multiply by, what's going to be on the numerator?
1. Secant x, tan x.
Cool, all right. Let's do it. What's going to happen?
Secant 1, secant 2.
Gone, almost gone. So we'll have secant x over tan squared x. You guys okay with that one?
Yeah.
Now here's an issue. If you try to do the secant x, that is going to give you infinity, isn't it? This is going to give you infinity. You probably could do another L'Hopital's if you wanted. However, sometimes it's worth your while. Isn't that infinity also? Infinity squared is still infinity, right? So it's worth your while to simplify as much as you can. So what I'm seeing here is that if I write this just a little bit different, if I write this as secant x, look at tan squared x is the same thing as cotangent squared, 1 over tan squared x, same thing as cotangent squared x. Are you with me on that one? We use some identities here. Well, what I'm seeing out of that one is that I could do 1 over cosine x times cosine squared x over sine squared x. This is our secant. You guys follow me on that one? This is cotangent squared. You follow me on that one? You with me still?
Yeah.
Can you simplify that?
Yeah.
Yeah, why not? Let's do it. Cosine, cosine squared. So yeah, we did a lot of trig in this one. I want to make sure that you guys are okay before I go on. You okay that this is definitely true?
Yeah.
And this is true, true?
Yep.
And this is the same thing as 1 over cosine. Hey, this same thing is, remember, if tangent is sine over cosine, cotangent is cosine over sine. So we have that. Simplify it. Now, let's just pretend we have a limit out front. If I do cosine of pi over 2, how much is cosine of pi over 2 again?
0.
How much is sine of pi over 2 again?
1.
I have 0 over 1. Is it okay to have 0 over 1?
Yes.
Then we've just evaluated our limit without having to do another L'Hopital's rule. Does that make sense? We kind of avoid this whole secant tangent thing and then 2 tangent secant squared. That's ugly. So make it easy by simplifying as much as you can. Not just once, as much as you can. That a lot of times makes your problem that much easier. Did you guys understand the concept here? Yes, you probably could do another L'Hopital. Should you? Probably not. Probably simplify as much as you can. So let's wrap this thing up. We've got and e. We've got a limit. We got x approaching pi over 2 from the left, and now we have, well, the only thing that we did, here's our star, we did our star, and now we have cosine x over sine squared x. Okay, let's do it one more time. You guys okay with going from here to here, yeah? What was cosine as we approach x equals pi? 0 over
1.
So this would be e to the
0.
Of course I said no, it's not always 1, and then I gave you an example that was 1 again, but just a coincidence, okay? So we get e to the 0 again, we get 1. Show of hands, feel okay with that one. That's a tough problem, it's tricky, that's a lot of stuff in that problem. Look at all the steps we have in that. Would you like to try one more?
Yes.
Okay. Ideas don't change though. Ideas are, if you have an indeterminate form, try to work with it. Make it 0 over 0 or infinity over infinity, and then you do L'Hopital's rule. After you do L'Hopital's rule, you simplify it every time. After you simplify, you check it again. And if you still have L'Hopital's rule, cool. If you don't, then you evaluate your limit. That's the whole idea. Okay. This one's going to take us a while too. Okay, now you really need to tell me what to do, okay? What would you do first? Try it, good. Let's do it. Let's plug in infinity and see what we get. What's 1 over infinity?
0.
What's 1 minus 0?
1.
And what's that go to?
Infinity.
So this is 1 to the infinity. Is that one of those indeterminate forms that I gave you in that little sheet?
Yeah.
So if it's that one, what should we try?
Oh, no, E.
The e to the ln thing. Why don't you do that? Go ahead and do the e to the ln thing. Notice I'm going to give you the shortcut right now. Of course, you can write this out and then write this out, but I'm going to do it in one step here. When you get the hang of this, this is absolutely fine. Just don't forget, oh my goodness, don't forget about the e. Okay, don't forget that e, it's important. So, what I know is that I could write this as e to the ln of this argument. Well, that's the same thing as pulling out the e, having the same old limit, having the x come down because I have an ln of the inside. Okay, I really do need to make sure that you guys are okay on going from here to here. Do you guys see that I'm basically doing the same thing, only in one step? Show of hands if you're okay with that one. Okay, that's everybody. That's good. So, same idea. It's still e to the ln, isn't it? And this is still an exponent, but I'm bringing it down. Okay, now let's check it again. Nothing really should change. I should have a 1 up there somewhere, and I should have an infinity. That's still infinity. Now this thing, let's look at that. That's going to change a little bit. Look what happens here. Here's an infinity. When I plug in infinity here, what do I get?
0.
1 minus 0?
1.
1 minus.
How about ln of 1?
0.
Oh, so I have infinity times 0. Oh, that's one of those indeterminate forms that I can actually work with. Isn't that kind of cool? When we do the ln, it changes from that that 1 to that infinity. That's cool. So, I'm sorry, to the 0. I misspoke. Which one would we want to move here, the ln or the x? Let's do that. So go ahead and do that. How do I move it? Do I just move the x to the denominator? What do I do? Okay, yeah, that's the way that we can do that.
Can you also say x to the negative 1? Or is it just the
Yeah, you can. I do that one because it's easy for me to see the limit of that. Sometimes I see x and negative 1, I think, oh, that's hard for me to think. I could do that again. But you can. Yeah, you can do that. So let's make sure that we actually have an indeterminate form. We already figured out that this one's 0. Let's look at this one. Remember, the 0 came from here. Well, okay, that's infinity times 0. So if I move an infinity to a denominator, the infinity changes from infinity to another
0.
a 0. Now I got 0 over. Do you guys see the 0 over 0?
Yeah.
This is 0. That's 1. ln of 1 is 0 over 0. Hey, what can I do every time I get 0 over 0? Why don't you go ahead and work on the L'Hopital's? This is going to be a little interesting, okay? A lot of stuff going on here. The denominator, fairly straightforward. We actually already did that one in one of the previous examples. So when I have 1 over x, of course, that's really x to the negative 1, as you said. Bring down the negative 1, subtract 1 from it, put over the negative 1 over the denominator of x squared. You guys okay with the negative 1 over x squared?
Yes.
Have you guys finished this one?
Yes.
Okay, so derivative of ln says, hey, 1 over the inside, where you're not changing anything. No problem. 1 over the inside times the derivative of the, now let's look at the derivative of the inside. The derivative of 1 minus 1 over, I haven't done this in a while, but it's kind of nice. So 1 over the inside times derivative of inside. I want you to see what happens here. So e. Limit x approaches infinity. We've got negative 1 over x squared. We've got 1 over 1 minus 1 over x. Times, what's the derivative of 1?
0.
What's the derivative of 1 over x? So if I have minus a negative, that's going to become, so if this whole thing gives us 1 over x squared, hopefully you understand why. The same reason this gives you negative 1 over x squared, we have minus a negative. So basically it's 0 minus negative, like that. That's really the derivative. Derivative of 1 is 0. Minus, minus. Derivative of this thing, hey, it's the same. It's negative 1 over x squared. Show of hands if you're okay with that one. So what that gives us in the long run is positive
1 over x squared. Square. And they cancel.
positive 1 over x squared. Okay, cool. Wow.
They multiply by the reciprocal of the denominator.
Simplify it, maybe.
I'd probably simplify it. I'd probably deal with this maybe.
Yeah.
Do y'all see that that's going to distribute across that denominator? So we'll get big fraction 1 over, looks like we get x squared minus x. X squared, there are other ways to do this, by the way. I'm just showing you one. So x squared minus x, this is negative 1 over x squared. All right. That looks a little better at least. We have fraction over fraction. We know that when we have a complex fraction like this, instead of having the division, we can always multiply by the reciprocal of the denominator. All right, well that's e. Man, just some algebra now.
Get back quick.
1 over, tell you what I'm going to do. Now, what am I going to do with that?
This should be the factor out the x.
I'm going to factor that, that's right. X times x minus 1. And I'm going to have negative x squared over 1. Division is the same thing as multiplication by the reciprocal. So I'm going to reciprocate. Now I'm going to simplify. What simplifies here?
The x. One of the x. And then the squared 1.
Okay, so this thing's completely gone. This thing's almost gone. And let's rewrite it. Let's see what we got. Remember, the idea is do L'Hopital's rule, simplify it, rewrite it, and then reevaluate. What's on our numerator?
Oh, x.
Close. Negative x. Denominator, I've got x. Okay, check it out. We're going to reevaluate right now. So take our infinity, plug it back in. This is what we do every time, right? Every single time we reevaluate. Hey, what's negative x as x approaches infinity? This is negative infinity, that's right. What's this as x approaches infinity? Okay, what's infinity minus 1? Like the little kids. I'm better than you by infinity. I'm better than you by infinity plus 1. Okay, that's still infinity. That counts. It's an infinity over an infinity. What are you going to do now? And that should answer your question. Can you do it more than once? Of course you can. Anytime you have, listen, just because it has an e on it, it doesn't matter. It's still a limit, right? It still falls into the whole idea of if it's infinity over infinity, do a L'Hopital's with it. So, we've got e to the limit of x approaching infinity. Everybody, derivative, oh, this is so nice. Goodness gracious. How much is that?
Negative 1.
Over
1. Negative 1.
So this is going to equal e to the negative 1. Or 0. 1 over e.
Sounds 0.
Oh.
So when we give our final answer, you want it to be in the notation of the limit as x approaches whatever, and then the answer, can you just bring it down?
This is literally exactly what you have every single step. This is what you should have. So you should have writing it as e with your function of x moving forward, then ln. You should be showing me all this work. You should be showing me this stuff, our simplification, getting down to here. Then you go, okay, this right here, this is still, you write a limit. Because when you do the L'Hopital's rule, that's your resultant of that. This is your derivative. It is negative 1. The derivative of this is 1. And then you go, well, hey, a limit of a constant is the constant, so no big deal. It just happens to be that limit of negative 1 is negative 1. E to the negative 1, just 1 over e. That's it. Should hands feel okay with that? Does it make sense, this whole idea? That's kind of a tough one, right? There's a lot going on that problem. But do you have any questions at all? Question?
On the second arrow right here, can you just like 1 over x squared over the 1 over x, can you just like cross like cancel those both out because they're products of each other?
These ones?
Yeah.
Yeah, you could do that. That's what I said. There's a couple different ways that you can actually do this. That would work out, I think, the same. Actually, it might be even a little bit better. Because if you did this, multiplied by the reciprocal, these are gone.
And that turns the
This thing right here, this becomes negative. This thing right here is 0, right? 1 minus 0 is 1. You just get -1. So yeah, same thing. I did want to show you this way, that way you understand, because we had a question earlier. Can you do a L'Hopital's rule again even if you have an e? The answer is yes. In this case you do. In the other case you wouldn't have to. Just like we had over here. Could you have? Yes. Did we have to? No. So we probably could have made this a little bit easier. Absolutely. But there's multiple ways to do these. My suggestion would be simplify as much as you can. I probably didn't do that here. Probably could have simplified that and made it just a little bit quicker. Be okay with that one?
Yes, sir.
This would be a great time for questions. Are there any other questions at all? So, do you know what I mean by indeterminate forms of limits? Indeterminate forms of limits, what's your goal? What are you trying to get?
0 over 0 or infinity over infinity.
Once you get 0 over 0 or infinity over infinity, what do you use?
L'Hopital?
That's right. That makes these limits so much easier than any other way that we have, okay, that L'Hopital's rule. Is L'Hopital's rule a quotient rule?
No.
Heavens no, oh my goodness, that'd be harder. This is just derivative of the numerator over derivative of the denominator. We look at the comparison of the derivatives of the functions rather than the comparison of the functions themselves, and the limits end up being the same. Last thing, are you okay that we can always do e to the ln of a function and it's still exactly the same? Okay, that's the idea.
Well, we always see it in that form.